Okay, now let's get on with our forces, and I want to look at electromagnetism as a gauge theory, because that provides a very straightforward way to understand a process which applies, as we'll see, equally in gravity, the weak interactions and the strong interactions. So we're going to start with the Dirac equation. And since I sigma 3 and gamma naught commute, you can put an extra I sigma 3 component, let's do it as e to the I sigma 3 theta, through on the right-hand side of this. It can commute through, and you will get a symmetry of the equation. Clearly, if psi dash is this rotated wave function, rotated by an e to the I sigma 3 theta on the right, then psi dashed is a solution of the same Dirac equation. But what if your theta is a function of position, x? And what you find when you calculate grad of psi dashed is you've got an unfortunate extra term, a grad theta times psi ri sigma 3 on the right-hand side, which spoils the covariance of the equation. What we're looking for here is an operator that can replace the grad to give you something covariant where solutions remain solutions after this rotation. So at the moment, the phase rotation does not work as a local symmetry. Why should we want it to? Basically from the structure of physical statements in the Dirac theory. And these are of two main types. You've got observables, such as the JS that I brought in, they're bilinear in psi, or you've got simple statements of equality, like psi is psi 1 plus psi 2. Now, both of those remain locally invariant. I can put in an e to the I sigma 3 times theta, where theta is a function of position, and both of those things would survive that, and they would still give you the same value observable or the same statement of equality between spinors. So it's only the derivative which has got a problem. So you've got to change the grad operator to get rid of unwanted terms and the gradient of R. Now, I'm going to express the results here in terms of just one further bit of notation, which is what we call the multi-vector derivative with respect to A. And basically, if A is a vector, A upstairs mu, E downstairs mu, then this dA is just like we had earlier for the gradient. It's E upstairs mu, D by dA mu. You can see that dx, or x of position, would just be the same as grad, but we can take derivatives with respect to any vector. And it's got these rather nice properties here. There's one I'll highlight at this point, that dA differentiating A through an R grade object returns this thing, -1 to the R, n minus 2R AR. N is the dimension of the space, R the grade of the object. So you'll notice that if you differentiate through a bivector in space-time, so n is 4, R is 2, you get 0. And it turns out, I mean, it's of course not obvious, this turns out to be key to why electromagnetism is a massless theory in 4D, and also one can use it to demonstrate how the Riemann tensor for a black hole works and gives a solution in gravity. Okay, so we can write our equation for grad psi dashed like this. Here we've taken d by dA of A dot grad. That's just a way of reassembling the grad. And psi times A dot grad of R. And it's the last term which is doing the damage. So we define a new operator like this. We define it as the original one, but plus 1/2 psi, and then we put something to the right of psi, omega of A, and we're going to figure out what omega of A has to be to make this work. And we want a new Dirac equation which employs this covariant derivative on the left-hand side. So let's actually carry out psi dashed equals psi r. So you'll have d goes to d dash. D dash should have the same form as d. And so for d dash, we're going to write it like this, where the omega is transformed to an omega dashed in such a way as to make everything work. And what you'll find pretty quickly if you go through this is that you need omega dashed to be r reverse, omega of A, r, minus 2 r reverse a dot grad of r. So this bit here is going to be of exactly the same form as the original omega, so it's just a rotated version. It's this new bit here which tells us what type of object we've got. And we can find out by differentiating r reverse r equals 1. Let's differentiate that with a dot grad. Then you get a dot grad r reverse r plus r reverse a dot grad of r equals 0, because 1 differentiated gives 0. And we see this bit here is the same as this. If you look at this line here, then you've got the thing we're interested in. When it's reversed, which is what's happening here, gives minus itself. So it has to be a bivector. So we've established that this thing that has to sit, I'll just go back, the thing that has to sit here in this covariant derivative has got to be a bivector function of A. It's called a connection, and technically you can think of it as belonging to the Lie algebra of the symmetry group, but we'll have more to say about that later. And in general, omega of A will not be expressible as a derivative of rota, and this is the essence of the gauging step, right? You take something arising from a derivative and generalize it to a term that cannot be formed this way, and we'll have a concrete example of that in a moment. So all of that was for a general rota R on the right-hand side of the wave function. And in fact, that's just done half of gravity for us. Okay, not just electromagnetism, but half of gravity. To get electromagnetism, we now restrict the rota to the form we first thought of with this phase change, e to the I sigma 3 theta. So let's work out what this is. Here's the object. The new bit is minus 2 r reverse a dot grad r. I won't go through the details. It's pretty quick, but you find that that's the same as a dot grad theta I sigma 3. And so this is the gauging step now. We've achieved this bit via derivative, a dot grad theta. What we do now is we generalize the form of this to a new object. And you can see we could do that if instead of a grad of a scalar, we put a general vector in that position. And that general vector is the 4 potential of electromagnetism, A. And we bring in a coupling constant at the same time. We call it lambda here, to write that omega A, this connection, is lambda A dot big A I sigma 3. And you can see that is indeed a bivector because it's I sigma 3, and it's a linear function of A. And under gauge transformations, the gauge field A must transform like this, right? And we would get no result from the curl of A. So curl of A would be 0 if we had it just as a grad theta, because the curl, and that is grad wedge, of grad theta involves a grad wedge grad, which they're parallel, if you like, and so, of course, you get 0. So it's only when curl of A is non-zero that you're going to get any genuine physical effects. The rest are gauge effects. So piecing that through, you put this new term in the equation, and you get this. Grad psi I sigma 3 minus EA psi, this is a new version of the coupling constant, is m psi gamma naught. And there we've got the Dirac equation with electromagnetism. Now, I've said that there's real physical effects when the curl of A is non-zero. How can I say that? Well, the next thing in a gauge theory is to work out the commutator of the covariant derivatives, because that's how you get physical things. And let's do it again. Let's go back to psi goes to psi r. If A and B are constant vectors, then you can work out the commutator dA dB acting on a general psi for these rotors at the right, and you find that all derivatives of psi cancel in this, and you get this thing over here to the right of psi, A dot grad omega B minus B dot grad omega A minus omega A cross omega B, in which all the derivatives of psi have cancelled. And that's the general result, which will see in a moment in gravity. But let's now restrict it back to this form that we have when we just got a phase term. And we know that omega of A is that. You put it in here, this bit here, the commutator of omega A cross omega B, that vanishes because it's just an I sigma 3 commuted with I sigma 3. So that's not going to give anything. And that corresponds to electromagnetism being what's called an abelian theory, where these bits of the connection cancel, and you're only left with this gradient bit here. You work out the gradient bit, and you find that it's equal to A wedge B dot F, where F is the curl of A, times I sigma 3. And so the conventional thing that we now do is we forget this is actually a mapping, an omega of A. We strip off the I sigma 3, and we think of F itself as being the field strength tensor. And of course, as we said, it vanishes if A is pure gauge. If A is grad phi, it just vanishes. Now, to get all the way through to the Maxwell equations, then you need to write down a Lagrangian field system, and that's incredibly simple. It's just minus half F dot F minus A dot J, where J is some external current. And you work out the Euler-Lagrange equations for this. You get grad F equals J, which, as you saw yesterday, is the full Maxwell equations, and you can get the usual four Maxwell equations if you write F equals E plus IB. So that's showing us how electromagnetism, we now have all the equations of it, emerges from the requirement to preserve phase invariance under local transformations. Okay, let's get to gravity. And so in gravity, we'll want to do something that is going to be as much as possible like the other three forces of nature. And we know all of these are described in terms of gauge theories. They're of a type, this business of the local scaling giving us a connection is called a Yang-Mills type gauge theory. And they're all in a flat space-time background. And so in the same way, gauge theory gravity is expressed in a flat space-time. The key question is then what we're gauging. And we choose this to be Lorentz rotations at a point, and the ability to carry out an arbitrary remapping from one space-time point to another. So this is rotations, in the Lorentz sense, and translations. They're the key things that we're going to be gauging. And again, it's much easier to work with the Dirac wave function as your starting point for this. And in fact, as I said, we're quite lucky because in the electromagnetic derivation, we've effectively already done the first of these, except we now want rotor transformations on the left of the wave function instead of on the right, because this is how the wave function responds to actual space-time Lorentz transformations. The R appears on the left, not the right. The things on the right, like the phase, are internal transformations of the system. On the left, they're responding to space-time transformations. Now, for the second, I won't go into the details of this, which was the arbitrary remapping of one space-time point for another, because thinking of it that it's translations, it's got a vector type appearance instead of a bivector type appearance, and you find you need a vector field which is a linear function of some arbitrary vector A. Now, I won't go into the details of this. I'll just show you very briefly a couple of examples of this. And again, as before, we get the field strength tensor by commuting the covariant derivatives. Here we commute them for the Lorentz field. And what you find is that, again, all the derivatives cancel out, and you get, applying this to some arbitrary multivector M, is in fact the Riemann tensor cross M. And here it is spelled out again. We've seen exactly this form from what we did before. That is the Riemann tensor. And it turns out you can make a fully covariant version, which is then invariant under the translations as well by writing this curly R of B is RHB. So we stick in an H, that makes it fully covariant. And this is a bivector function of bivectors. You can see the output as a bivector, and it's just like the inertia tensor, as Leo was just, of the type Leo was talking about before. It's a mapping of bivectors to bivectors. And then you can set up what you need for your Lagrangian, and for that you take dB wedge dA dot of the Riemann tensor. That gives you a scalar, and the simplest gravitational action you can use, this corresponds to what's called the Einstein-Hilbert action, and was how general relativity was first derived as via Lagrangian, like this. You take the determinant of this vector function h multiplied by r. And that's it, basically. We first did this back in the 90s, and there's a full description in this paper here. What theory do you get in this way? Well, basically, it reproduces the predictions of an extension of general relativity known as the Einstein-Cartan theory, which incorporates quantum spin. You can see that's going to happen because we started with the Dirac equations, so of course we're going to be able to incorporate spin. But basically, because it works in this gauge theory sense in a flat background space-time, it differs on global issues such as nature of the horizons and topology. A big advantage is that you can be very clear what the physical predictions of the theory are, since it's a gauge theory, and the physical predictions are those that are gauge invariant. I've already said it's conceptually simpler than standard GR, since it works in a flat space background, and I think it's very important that in a practical sense, if you have a Clifford algebra program that can do, a computer algebra program that can do Clifford algebra in space-time, then you can immediately start exploring gravity. You don't need tensor calculus or any extension to curved space. You can do all of the gravity that you need just with this. And again, to emphasize the simplicity, in the absence of matter, here are the equations. It's dr of this Riemann tensor equals 0. This is a full Clifford product here, so it's got both trivector and vector parts, and the curl of this translation field is 0. Now, I'm going to give just one example of how things look in this, which is taken from the set of 3 that I looked at last time. And basically just want to say, how do black holes look in this approach? And it becomes exactly like you would do in electromagnetism when you're setting up equations for a point charge. You need to choose a gauge and work from there. And the gauge here, we're going to do it in terms of a choice of h function. We want to cover all of flat space, except, of course, possibly a singularity at the origin. And just like in electromagnetism, where you choose different gauges, you'd expect the field strength tensor to be the same and not to depend on the choice of gauge. Well, how does that work out? Going to have ER as the unit radial vector, ET equals gamma naught as the unit time vector, and you can then define a radial null vector, which we need in one of these forms, as E minus equals ET minus ER. You can see that's null. And then here's 2 good choices for this H function. The first we call the Newtonian gauge. A lot of the physics looks very Newtonian-like in this gauge. And we have H of A as A minus the square root of 2m over r, A dot ER ET. Pretty simple. And then there's another type. I wanted 2 gauges so I can show you they lead to the same Riemann tensor. A plus m over r, A dot E minus E minus. This is the gauge theory gravity analog of the advanced Eddington-Finkelstein metric, and is very good for treating the paths of null things like photons. If you work out the Riemann tensor from those, they both give this form here. R of B is minus m over 2r cubed, B plus 3 sigma r, B sigma r. And you can see that this is going to return you a bivector, because here we've just got the bivector coming back, but here we've sandwiched it in sigma r. That's going to give you another bivector. So it is indeed a mapping of bivectors. And you can immediately check this field equation I talked about, using the results for the dA derivative above. then you should have a look through this, and you'll see that you take dA of, for this bit, A wedge B, and for this bit, 3 sigma r A wedge B AR. And you unwrap it so it got explicit A's here, and you can see this bit here, dA sigma r A is going to return 0 from what I said earlier. And you get 0. So this is really very impressive as regards to compactness and ease of working. Now, just to finish on the gravity bit, is the correct theory of gravity just based on local invariance under rotations and translations or is there more? And I personally think that we want to bring in further invariance, that is scale invariance, the ability to carry out an arbitrary rescaling of lengths at each point, that this should be a further invariance of gravity. So we can rotate, we can translate. What's the other thing that we might want to take from conformal transformations that's a continuous thing you can do, that's scale invariance. And with colleagues, we've now developed a new theory of gravity where all the elements of the Lagrangian are indeed invariant under scale changes. And you find that this means you've got to include what's called torsion. This is a bivector valued function of position. It's not a new field. It's part of the connection we already talked about. But where it shows up is it modifies this curl of H equals 0 equation to this. Curl of H is now S of H of A, where S of A is this torsion. And the torsion and the scale invariant nature of the theory, we believe, is actually crucial in understanding the origin of the cosmological constant. You've probably heard many times that the cosmological constant is one of the most glaring problems in physics. If you think it's provided or comes from, the cosmological constant is meant to drive the expansion of the universe at the moment, makes it accelerate. And where's that coming from? It could be vacuum energy, but if you work out the vacuum energy that you would get if you interpreted it naively from particle physics effects, so the sort of boiling vacuum of particles being created and destroyed, it turns out it's about 10 to the power 122 times bigger than the actual cosmological constant, which we now observe. And so it's very hard to see how that could be a good explanation. But you find in this approach here that if you have a constant time-like torsion of this form here, so the bivector field S of the vector A is A dot I gamma naught, right? This is a trivector, so A dot that is a bivector. Q naught's just some scalar constant. This can provide a late-time dynamical effect in cosmology, which precisely mimics the external vacuum energy. And you find also that as the universe develops, it does actually go to having this type of torsion at late times by itself. So there's a couple of papers you could look at here which explains this. Unfortunately, for current purposes, both of these are written in conventional notation, but you will find in the second one here a section written in GA which explains all the different types of Lagrangians that we combine to get scale invariance. So all the possible scale invariant ones, there's about 6 of them, are put into this theory, and that's explained there in GA terms. Right, now I get, now I get to Octonions. So, is everyone brave enough to carry on at this point? Okay, right, so let's say some things about Octonions generally to start with. So they were first introduced as a generalization of quaternions by Graves in 1843 and Cayley in 1845. Now, I say that Graves introduced them in 1843. Unfortunately, his first actual paper concerning them wasn't published till just after Cayley's paper in 1845, but he's generally given credit for coming up with the idea first. And I find it rather amusing in its way to look at both these initial papers. Here's the start of Graves' paper, published in, basically it was the Philosophical Magazine. of the Royal Society. And it's about the connection between the general theory of normal couples and the theory of complete quadratic functions of two variables. Neither of those are anything to do with octonions. And the octonions were only mentioned in a PS to the article. And here is his PS, which is expressing how he thought of them. And he thought the most important thing was this theorem here. The product of two sums of 8 squares is a sum of 8 squares, which he had managed to prove in terms of these new numbers, the octonions. And we'll come back to this theorem below. And it's also interesting, the slightly earlier paper by Cayley in 1845 was about the quite different subject of elliptic functions, with the octonions only occupying a postscript, right? So they did things differently in those days. You could put in postscripts on some totally new thing, and it would be fine. As we've already said, the key features of octonions is that they form a norm division algebra. Any product of octonions has a norm which is a product of the individual norms. And two non-zero octonions always multiply to produce a further non-zero octonion. And the only norm division algebras are complex numbers quaternions and octonions. And I've already said this, that the octonions have this feature that they're neither commutative nor associative. And so in particular, there's no general rule that AB times C is the same as A times BC. And it differs, of course, fundamentally from the geometric product of GA in this regard. So how is it that they could be useful in physics, and how we're going to be able to represent them within GA? We're going to use the STA. The key is that in the STA, Dirac-Spinner's psi can be divided into parts that commute or anticommute with the unit time-line vector gamma naught. So basically, the sigmas and the I that we had before, so 3 sigmas and I, they anticommute with gamma naught. And the Pauli parts, the scalar and the I sigma I, they commute. And so what we're going to do is, for a general psi, we're going to define the even part, psi plus, as a half psi plus gamma naught psi gamma naught, and the odd part is a half psi minus gamma naught psi gamma naught. And these correspond to the even and odd parts of the full Pauli algebra. And here it is. Here's the answer then for how we multiply two octonions, psi and phi, which to us are Dirac spinors, to get a new Dirac spinor which has the properties we need. It's to do this. We're going to call the operation of octonionic multiplication star, and the new spinor is given by this. It's the product of the even bits. Then we have phi reverse odd part times psi odd part plus phi odd psi even plus psi odd reverse of psi plus. That turns out to give us the full octonion multiplication. And you should note carefully that the 4 individual products here, they're all usual geometric products taking place within the ordinary STA, and the reverse here is just an ordinary STA reverse, and the spinors are just ordinary STA spinors. Hence our claim about being able to compute everything entirely within the STA. Now, from the form of this, you can see such a product is highly unlikely to be associative. Indeed, in general, it's not. The property it does have comes from essentially the defining property of the octonions, that they form a norm division algebra. Now, we need the norm, so we need to define a conjugate element which we can multiply in to get the norm. So we're going to use star to denote conjugation, and it works like this. Psi star is the reverse of the even part of psi minus the odd part of psi. And just with that, and our definition of the product, you then find the following norm. The norm of psi, which is psi octonion product with the octonion conjugate, turns out to be this. It's a half gamma naught psi reverse plus psi gamma naught psi reverse gamma naught, which I'll recognize as the Dirac current, okay? Which is extremely intriguing. And we can see this makes perfect sense as follows. We know from its interpretation as a probability current that J is always non-zero and future pointing as long as psi is non-zero. So this thing here is always going to be positive, which you need for a norm. And it's a scalar, and so it coincides perfectly with the properties a norm should have. Well, there's one more property we need to verify. That is that the norm of a product is the product of the norms. Okay? It's got to respect multiplication. And so here we have the norm of psi producted with phi should be this product of norms there for all Dirac spinors psi and phi. And given our definitions so far, this is a matter of computation, right? We just work this out within the STA and see if it works. And it does, okay? So we have indeed instantiated this norm product. And given our reinterpretation of the octonionic norm in terms of Dirac current, you can see with theta as being the product, it corresponds to this ordinary STA result that theta gamma naught theta reverse dot gamma naught is the individual, it's the product of these individual Dirac currents, time-like components just there. And now we can make contact with that PS of Graves, because we've emphasized earlier that the Dirac current is the sum of 8 squares. If you remember, the A0 squared plus A1 squared through to B3 squared. And so this is a sum of 8 squares. This is a sum of 8 squares. And what we're saying is that their product is indeed another sum of 8 squares, which is very nice. And I find it quite startling that Graves could write down something in 1845 about the product of 8 squares product of 2 sums of 8 squares is a sum of 8 squares. And suddenly we find out 150 years later, basically, that that is telling us something profound about the Dirac current. Okay. Now, here's what the multiplication table for the octonions looks like in a particular form. Unfortunately, you can have multiple forms that are possible. This is what I've given you here is the one corresponding to the influential review of octonions by Baez, and is also that used by Cole-Fury, who I mentioned earlier. And I'm going to refer to some papers as we go along. I've got references all at the end, so they'll all be visible at the end of the talk. And this table, unfortunately, is just one of 480 that you can use, so there's another 479 possibilities. It's better not to look at this table, but to look at the Fano plane representation of octonion multiplication. And just look at, first of all, at the things on the left-hand side of each assignment. So there's E6, E4, E7. These are the octonions which are not E0. E0 is just 1, we can think of it. It squares to itself, all right? Go down that diagonal. It squares to itself, and the E1 squared gives minus E0, E2 squared gives minus E0. So all these things here, they're like generalized quaternions in that they all square to minus 1. And indeed, the first part of the table you can think of as a quaternionic table, but then we extend them with these extra bits. And this is a mnemonic for being able to figure out how to multiply them. If you follow the arrows, E6 times E1 gives you E5, and the same for all the other arrows around here. Now, how do we assign these to STA elements? Well, I've done it here in such a way that the pseudoscalar, which I feel is distinguished, is in the middle here at E7, and then these three are the midpoints are the I sigma 1, I sigma 2, I sigma 3, and the ones out here are the sigmas. So that's how I've chosen to set up the correspondence with the STA. Now, we've already said that fundamental forces appear to work via localization of global symmetries. This introduces new forces, and the way of introducing new fields which give the forces is the same for electromagnetic weak and strong forces. Go via this procedure I've already shown you with the connection, and the Lorentz rotation part of gravity. So we already know how to do all that bit entirely within the STA. So the starting point for understanding a force now, because we don't need to worry about the gauging aspect, that's all clear, is to identify the global symmetry we think should be obeyed. And the best way to express this is via a group. There are a lot of groups. How do we or nature pick out the ones which are relevant? And what we would like to move towards is understanding the gauge groups at the heart of the standard model of particle physics. This is what they are. It appears to work with a direct product of groups SU3 cross SU2 cross U1. And can we find these emerging from some general principle? Well, here I want to look at what Octonions have to offer in this direction. And as I say, this is going to be following what Cole-Fury and others have particularly emphasized as regards the role of chains of Octonian operators. And this is a clever technique where you use sequences of Octonions to pack in a great deal of information despite the relatively small size of the spaces involved. And here, the non-associativity of the Octonions is crucial since, okay, suppose we have a chain with B, so we take phi times B multiplied at the left, and then we use A as the next thing in the chain. That does not have to be the same as AB acting on phi. Because the lack of associativity. So having no associativity is actually a benefit here because we can start building up some complex chains which are not just the same as piling everything together. This process does not go on forever, and you find that 7 left multiplications or 7 right multiplications, if you're doing it on the right, is the maximum you need to consider. And that means that if you consider purely left multiplications, then you can consider sequences with a maximum of 6 of these. And Fury and others show that this is isomorphic to the 6-dimensional Clifford algebra CL06. It's got 6 grade 1 objects squaring to -1. And so we call that anti-Euclidean Clifford algebra. Now, maybe I should skip a bit here, because I really don't want to go on far too long. But the fact that we can have something isomorphic to a Clifford algebra, we can understand quite well from the STA viewpoint. Basically, what we need to do is show that if we have a chain, EJ times phi, and we do another thing with an EI, that's the same as minus EJ times EI phi, where this is when I is not equal to J. And if we had the same I or J, we'd want this to give minus phi. So I've got this here. Yes, this will do. EI star EJ star phi should be minus phi equals J, and minus EJ star EI phi for I not equal to J. And I hope you can see there that we've encoded the basis elements of a Clifford algebra with this signature of 6 minor signs. All right, so this, we can define a vector as a map, phi goes to EI star phi, and then we've got the defining relations for unit vectors in the Clifford algebra. And of course, we know that each of these multiplications can be done just in the STA. And so each of these things is a defined map of an STA even grade element to new spinor. And the definition, that's because the definition of the map can be written down entirely in the STA. So what we've achieved is by a 4D Clifford algebra acting on itself, i.e. the STA with a total of 16 elements, we've generated a 6D Clifford algebra with 64 elements. And this is exciting because it's big enough to encompass the entire standard model of particle physics. Right? So let's look briefly at the standard model. So you probably know most of this already, but here are, on this side, the fermions. These are spin half things over here, and they're divided into the quarks, of which there are 6, and leptons, of which there are 6. Basically, you should look down a column here. Look at the column 1. This is called the first generation of particles. We have up and down quarks, the electron and the electron neutrino. Second generation, charm and strange quarks, muon neutrino. And then top and bottom quarks, tau and tau neutrino. So that's all, as it were, the particles. On this side, we have the force carriers, which consist of the gluons, which mediate the strong interactions between these quarks, the photon for electromagnetism, and the Z and W, which go with the weak interaction, and then the Higgs, which, as you, I'm sure, heard about, effectively gives mass to several of the otherwise massless particles in the standard model. The thing I'll draw your attention to here, this is a count of all the particles. The gluons work by exchanging colors. This isn't a good word. We arbitrarily assign colors to the quarks. So each of these here, so this up quark comes in 3 different colors, red, green, and blue. They're just labels, right? They don't actually mean anything in terms of colors. And there's also an anti-quark, an anti-up. And so if you just want to consider the up quark, you've got 6 objects, okay? The 3 colors, and then the anti-version of it. The gluons, it turns out there's 8 of them. And basically, I've got a numbering here, which shows you, right? So we had 2 types of quarks, up-down type, multiplied by the 3 generations. Each has 3 colors, so you get 36 for them. There's 12 leptons, and then for the forces, you can go down this list, add it all up, you get 61 particles. And so people have been definitely very interested in the idea that the Clifford algebra, CL06, which has 64 elements, could be able to represent all the particle states that we need in the standard model. And with a little room to spare, but not too much. So there's not too much room for any extra particles in this. And indeed, Gording and May, in an article actually in Advances in Applying Clifford Algebras, do this. But unfortunately, they do it entirely in terms of 8x8 complex matrix representations of CL06. And it makes it very difficult to link up to a geometrical approach. So what can we do in terms of using what we've already got to represent these particles? And what I'm going to do is just take a small part of the structure to show how things work in the STA approach. And basically, what we're going to show is that for the strong force, which is carried by these gluons and which glue the quarks together to form the protons, neutrons, and various mesons of particle physics, the underlying group is SU3, and we're going to understand that in terms of what we've got with octonions. So let's see what... Yes. Okay, so what does SU3 mean? Let's just get clear on that. The unitary bit means that in matrix terms, U times its complex conjugate transpose is 1. And the special unitary group is that you eliminate 1 degree of freedom by demanding that the determinant of the matrices, when you're doing it in matrix terms, is equal to 1, right? So we have 8 possibilities. We've got 3 by 3 complex, gives us 9. and we take out one of the states by asking that the determinant is 1. So there are 8 such states within SU3. And in particle physics terms, these are the 8 gluons we were just talking about. So all that's how it be viewed standardly. Now here comes the bit which is not just standard particle physics. We're going to embed SU3 within a larger group. It's going to be the exceptional Lie group G2. And so we need to know what exceptional Lie groups are. And these stand outside the normal classification of groups into an infinite series of 4 different types. And you'll be familiar with some of these. The 4 different types are A, N, B, N, C, N, D, N. And you could have N equals all the way up to infinity. And 2 of them, which I recognize, I think most people would, are the alternating groups AN or the dihedral groups GN. But there are 5 groups which stand outside that classification. And they're shown in bold on this diagram. Sorry, this is a bit complex. But these ones here, E8, E7, E6, F4, and then we zoom over here and we get to G2. These are the exceptional groups in the Lie classification, and they're all finite in terms of dimension. And they, as I say, stand outside of this classification in terms of the infinite series of other groups. G2 is the smallest of them. It's got 14 dimensions. And as you may be able to see here, these lines indicate subgroups. It's got SU3 as a subgroup. And what we're going to do, we're going to use the extra dimensions of G2 relative to SU3 to accommodate a quark. We've said that comes in 3 colors. Each has an antiparticle. So for a single quark, we need 6 states. And this works because G2 is 14-dimensional, SU3 is 8-dimensional. Now, possibly, this is all part of a grander scheme. And just an example of that, if you look near the top here, standing pretty near the top is SU8. It's a subgroup. You come out of E8 down to E7 and then to SU8. And this thing, I've now got working completely satisfactorily within these octonionic chains, i.e. within the STA. And so it is possible that we can go much higher up this chain and maybe all the way to E8. It's quite a way. This SU8, which is now completely decoded using this, it stands quite near the top. It's got 63 dimensions, which is, again, quite nice for the standard model. But if we went all the way to E8, that's 248 dimensions, and E7 is 133 dimensions. So clearly, it's not going to fit into just what we've got at the moment. Anyway, just want to say that in terms of SU8, that's it's got a rank. Sorry, this is going to probably attempting to get in too much quite at this point, but the rank of a group, like in G2, the subscript is the rank. In terms of E8, the 8 is the rank. What does it mean? It means the number of mutually commuting vectors. All right, so it's a maximal set of mutually commuting objects. In this SU8 thing, here's the maximal commuting set expressed in terms of these octonionic chains, right? This is completely explicit. Each of these, it is commuting with all the others. Now, quite remarkably, I mean, I played with these for a long while. I eventually figured out what they were when you translate them through to the STA. They're incredibly simple. These are reflection in gamma naught, reflection in gamma 1, gamma 2, gamma 3, sigma 3, sigma 2, and sigma 1, right? Which is incredible to find something that simple underlying something apparently so complex. And you can see immediately why they intercommute, because although, say, gamma 1 does not commute with gamma 2, if you do it each side, you get 2 sign changes, and then it does commute. I'll skip that. This is a nice picture of what's called the root system of E8, showing the incredible complexity of these objects when you get up to these higher dimensions. Rather amusingly, this was done with actual pins and threads. Someone had made this version out of cotton and pins, but it's very beautiful. Okay, we're going to just stick, for this final bit, with much more humble things. We're going to deal with SU3, which has 8 gluons, 1 quark and 1 antiquark, and we're going to understand how we get this in terms of G2. And it's just going to be what we said. We're going to use something that preserves the time-like portion of the Dirac current, because we have to preserve the octonionic norm. That's the same as preserving the time-like component here. And you get SU3 by restricting this psi here to being just the bivector f. Right? Psi is a bivector plus a pseudoscalar plus a scalar. We're going to pull out the f bit and ask what would preserve that. And you can read off some of the transformations by I. So consider, let's just put f here. Suppose I did a double-sided rotation, R reverse, where R commutes with gamma naught. You can see straight away from this, the R will pass through the gamma naughts, and you'll get something that is just invariant. So such rotors are the spatial rotors, forms a 3-parameter set, and accounts for 3 of the SU3 generators. That's straightforward. There's another 3-parameter set, Fij, that looks like this in terms of the transformation. And then to complete the set, there are 3 generators, Ji, that work like this. X of alpha Ji f as an operator is cos alpha f plus sine alpha I sigma I f sigma I. So you reflect in that and multiply by I. And that gives you 3 lots of 3. And the restriction that brings it down from U3 to SU3 is that this sum has to be 0. And what I invite you to do, when you got the slides, is demonstrate that these transformations I've just told you actually really do preserve gamma naught f gamma naught. And if you do this, you'll have been able to understand the finite rather than infinitesimal forms of the SU3 transformations. And you do it just by fairly simple manipulations in the space-time algebra. And doing that with the finite forms, we've considered really quite advanced in the usual matrix approach. And then you ask, what are the obvious next things to do as regards gamma naught psi, gamma naught psi reverse? Let's put psi to be the remaining bits. There'll be e to the I beta type transformations. That's your global U1 for the next group that you find within the standard model. Or you could use single-sided rotor transformations of psi, like psi goes to psi r, just like we did earlier, where r needs to be a spatial rotor and commutes with gamma naught, that's SU2. So you can read this off as obvious things and find that structure. Now, finally, what about getting the quarks and representing the whole thing? That comes from identifying some operators here, of which there are 21, called JMN, where M is 1, 2, 3, N is 1 to 7. This corresponds to the set of Octonian imaginaries. And this here is the dimension of a set of things that are all mutually commuting. For a given N, all these JMNs are mutually commuting. And it turns out you can more or less directly write them down. You remember the E6 had the STA equivalent sigma 2. You find that you combine these reflections we already had, which I talked about just now, with sigma 2. And you get these things. And it's obvious how these mutually intercommute, because reflections always commute. And then you've got a sigma 2 outside, which also commutes. So using them, you then define 7 objects here, which are differences of 2 of them, and another 7 objects, which are differences with respect to the third one here. And it turns out that the first 7 here are SU3 generators, and M7, the last one of those, is the missing 8th generator. and the mi for I from 1 to 6 are the quark states. And you can immediately identify these things with the Gell-Mann matrices, which people use to do the SU3, and you can put the others together to get the quarks in this form here. The red, green, and blue quarks are these pairs of quantities here. You have M3, M1, and then the antiparticle is M3 and minus M1. And how do the gluons, which are these things here, these are the 8 gluons, how do they interact with the particles? They just operate on them directly via the usual GA product. So what you find, sorry, I rushed that bit because I really do want to finish. I'm sure you do as well. But this gives a complete mapping of the color force and some of the particles it's operating on. This quark with all 3 colors and its antiparticle. And you'll see that you've got 7 plus 7, which is 14 dimensions, and that turns out to be exactly this group, G2, that is the lowest exceptional group. So I'm currently seeking to find the best way of incorporating SU2 weak forces, and hopefully this will look as simple as the above in STA terms. You saw that when we got to the crucial quantities, there was a real pattern to what the STA equivalents looked like, and in particular, the mutually commuting objects, they all worked via reflections, which was very clever. Right, so basically what's particularly nice about what we've got so far is that anyone has a computer algebra program which can do the space-time algebra. And you can do that, for example, if you can do the conformal geometric algebra of 2D space, they can now do the Octonions as abstract entities, and they're a lot of fun. Or you can explore the color force between quarks. And I hope to get further in the sense of having much more concrete examples that everyone can try out and encompassing more of the particles and more of the forces soon. So there's some last bits here about some problems that we need to sort through and get right and ideas for future work, but I'm going to skip that now. You can see them at a later time. Thank you very much.